Good afternoon. So I'm looking at here problem 36 from section 8.3, and we're asked to solve this initial value problem. And they don't specify it here, but it is in the section on Laplace transforms. And because I see that there are step functions involved, I'm instinctively going to try to use the Laplace transform. And so what this really looks like on the right-hand side, notice it is 0 up until time pi, and then is 0 after time pi. And during that, it has value 1. So my forcing function, sort of what's happening is, as time begins, there's no forcing function there, but then for a few seconds, I'm going to give a unit impulse to this problem, and we'll see how the motion responds. So if you notice the left-hand side, we've seen this sort of thing before. Often we might use the x dot notation if you think about an oscillating pendulum or spring. And so we would expect, if it was a homogeneous equation here, this would be an undamped solution, so we would expect something that looks like a sine or a cosine that is possibly shifted. But let's see what happens when we affect it within its run. So to do this problem, I'm going to take a Laplace transform of both sides. So when I take the Laplace transform of the left-hand side, the Laplace transform of x double prime, right, turns into s squared capital X. So I'm going to use the symbol for capital X. And then we subtract off s times little x of 0 minus little x prime of 0. And then let's take the Laplace transform of just the x, so we get another capital X in this problem. Now on the right-hand side, since there are two step functions separated by some subtraction, I'm going to take advantage of the linearity and just do the Laplace transform of the first step function and then the Laplace transform of the second. So the first step function gives me e to the minus pi s divided by s. And then I'm going to subtract off the transform of the next, so e to the minus 2 pi s divided by s. Great, so there's our first step, and now we're going to go ahead and solve for capital X and plug in the different values. So this goes to 0, and this goes to 1. So my left-hand side, I'm going to do a little bit of rearranging here. I'm going to bring the negative 1 to the right-hand side, leaving only x squared times times s squared plus x, which can be written like so. That will be equal to, on the left-hand side, which is now this, but with a plus 1 on that side. Great, so now I will solve for x completely by itself. This then gives me e to the minus pi s over, and I could write this in a few different ways if I chose. I could write it with an s squared plus 1 beneath each. That's one option. Plus 1 over s squared plus 1. I could have combined these beforehand if I chose it to be 1. But what I'm going to take advantage of here is how there is some similarities here between both of these denominators. And so if I decide that I need to do, for instance, partial fraction decomp, I could really focus on doing it for just one of these denominators and then use the results for both. So that's what I want to do. So again, I'm going to focus on doing partial fraction, just one of these denominators. And maybe I will do that in green here. So let's think about this. Let's think about, so a little side work here, a little thought bubble. 1 divided by s squared plus 1. I want to write that as two different fractions, so a over s plus, notice this is irreducible, so I will need a bx plus c. So to do the partial fraction decomp, I'm going to multiply them back together and make the numerators of both sides of this equation the same. So this will turn into an as squared for all my s. Oops, excuse me, that's a bad habit I have. I just noticed I wrote bx. That should be s since we are now in the s domain. Every time I teach this, though, I use x's. It's just a bad habit. So then I will also have a b s squared. So I'm just looking at what has the s squareds. I'm going to put those first. Going through what will have an s with it will just be a c times s. And then what will be a constant is just the a. And this has the same denominator. Notice this makes our job pretty easy. There's no s's on the left-hand side, and the constant is 1, so that gives you c is equal to 0, a is equal to 1. But then here the a and the b have to cancel, so b would be negative 1. So that tells me I could rewrite my fraction here as 1 over s. Perhaps you can write it as minus s over s squared plus 1. So I'm going to take advantage of that green thought to rewrite the white equation at the top. So that white equation says I could rewrite x as, let's think about what is with the e to the minus pi s. I'm just going to think about it as a fraction. So it'd be multiplied by 1 divided by s, and then s over s squared plus 1. So those are each, it can be distributed across those. Then likewise, here with the e to the negative 2 pi s, 1 over s minus s over s squared plus 1. And then the last, I am leaving exactly as it is. So the reason we're doing this is we're trying to separate things out enough so that we can do an inverse transform. So using the table in the back of the textbook, I'm getting pretty close. If you prefer, you can rewrite each of these with the e term as well, but it's not necessary. So what I'm going to do now is think about how can I do an inverse transform of each of these, right? So I need to take the inverse transform of this capital X, and I would have my solution as soon as we do that. So I look at my table, and I see there that I have, looking at property, I would say 18. If I call, maybe I'll do it in blue, this capital F, if I can find my lowercase f, then I can use property 18 to rewrite this first term as it would be lowercase f of t minus, in this case, we're subtracting off the a, so the pi up there. So t minus pi times the step of t minus pi. So that would be that first whole problem or term. If I considered the yellow, so notice this would be the same capital F here. So I would then subtract off, again using property 18, f, but this time t minus 2 pi, step t minus 2 pi. And then maybe in red for this last one, I could actually just do this one as it is. So 1 over s squared, we have s squared plus 1 here. And so I look at my table, and that looks a lot like property 5, right, which would have b equaling 1. So this would give me then, for the red, plus sine of t. So this would all be pretty much finished if we know what little f is. So let's find that real fast. So here's a little side work. Maybe we'll do it over on the left. So recognize the inverse Laplace transform of this capital F would be, well, the inverse Laplace transform of 1 divided by s would just be the number 1. And we subtract off of that, well, the inverse Laplace transform of s divided by s squared plus 1 is, looking at my table, that's property 6. So I would subtract off cosine of t. So this is my little lowercase f of t. So we just now need to substitute that in and simplify things. So 1 minus cosine of t. So let's do this. So for the blue, 1 minus cosine of t turns into, so we're going to have the quantity 1 minus cosine of t minus pi, though I have to substitute that in there, right? Step of t minus pi. And then likewise, I'm going to subtract off of that 1 minus cosine of t minus 2 pi. Step of t minus 2 pi. And then the sign is just coming along for the right. Great. Then we're going to go ahead and just do a little, I mean, this I guess could be done, but you can write this out a little bit nicer. Noticing that cosine of t minus pi, there's an identity there for that. You can also have an identity here for t minus 2 pi. So I could rewrite this, if I chose, in a bit of a nicer way. And maybe I'll do that in the color white here. So I end up with 1 minus cosine, and this could really be a curly bracket at this point, or I'm sorry, just a normal parentheses. So cosine of t minus pi will become plus here, cosine of t, step function t minus pi, and then we have minus 1 minus cosine of t because it's periodic, step, let me scoot over a little bit here, function t minus 2 pi, and then plus sine of t. Great, and that's something that might be worth just sticking into Desmos and seeing what it looks like. We can go ahead and do that. So I just plugged it in here, and it turned out to be a little bit more annoying than I had anticipated, just because I have to create my own step functions in Desmos, and sometimes, as in this case, it tried to, what do you call it? It interpreted changing the argument as multiplication. So Desmos is sometimes weird, but this is what your solution will look like. So this is your lowercase x of t.